Hello, and thanks for clicking on this next Prenarculus production. Today we're going to be talking about inverse trig functions and how they relate to the unit circle. So we've already talked about inverse trig functions before when we worked with SOHCAHTOA, when we were given a ratio and we wanted to find an angle. But now we're going to do the same thing, I guess, but we're going to use the unit circle to work with it. Okay? All right, so let's talk about a couple things. So, first things first, we already know what an inverse function is, okay, and what it does. Basically, an inverse function, it switches the x and y coordinate. All right, it switches the x and y coordinates on an ordered pair. Okay, that's exactly what it does. All right, we learned that back at the beginning of the year. So now we want to apply that concept to trig functions. So let's first talk about what we did when we worked with SOHCAHTOA. So when we worked with SOHCAHTOA, we did work a little bit with inverse trig. So let's say we had an angle theta, okay? And let's say I labeled a couple sides of it. We'll call this side 1 and this side 4. Doesn't matter. We could use SOHCAHTOA to create our relationship. From theta, we have 1, that's opposite. And then we have the 4, that's the hypotenuse. So opposite over hypotenuse, that's sine. So sine of theta we know is 1/4. And then if you remember back, to find the angle theta, we had to find the inverse sine of 1/4. Okay, we had to have the inverse sine of 1/4, right? And then in our calculator, that gave us the angle that we were looking for. Okay, so basically when you work with inverse trig, you're going to work with a ratio, and that ratio is going to yield for you an angle measure. All right, now we can certainly see how that concept would apply here to the unit circle. Our unit circle has angles on it, and then it has a lot of ratios, right? So basically what we're going to do is we're going to work with those ratios, and then you're going to have to give me the angle from the unit circle that it belongs to. All right, and that's basically what we're going to try to accomplish here. But it's a little more complicated than that being that simple. Okay, there's always something to make it more complicated in math. So let's talk about the graph. Well, we're going to talk about the inverse sine function here. But first, let's talk about the graph of y equals sine x. So the graph of y equals sine x, we graphed that a lot from 0 over to 2 pi. Looks like this. Okay, middle, high, middle, low, middle. We did this a bunch. All right, that's the graph of y equals sine x. Now, if you remember back, we talked about inverse functions. When we talked about inverse function, for a graph to have an inverse function, the graph must pass the horizontal line test. It must pass the horizontal line test. The only problem with this graph is it doesn't pass the horizontal line test. It fails it. So does that mean that my graph of y equals sine x doesn't have an inverse? Well, not necessarily. Okay, it still can have an inverse, but we have to be selective about some of the angles that we choose. And here's what I mean. So let's say I were to ask you for the inverse sine of 1/2. So my x coordinate is going to be 1/2, and I want to know what the y coordinate would be. Well, the inverse sine of 1/2, well, what angle has 1/2 as its y coordinate? Well, pi over 6 does. And technically 5 pi over 6 does. We agree? So I'd have to go over 1/2 up pi over 6, and then over 1/2 up 5 pi over 6. Now, the issue with that is if I go over 1/2 and up pi over 6, let's say, and then up 5 pi over 6, here's the problem with my inverse sine function. It fails the vertical line test. So it's not a function. What I want to try to do is I want to try to create this inverse sine function so that it's actually a function. Now, the reason this is not a function, if I'm using this idea, is because I have two angles that have the same ratio, right? My ratio is a half, but there's two angles that have a ratio of a half on the unit circle. So here's what we're going to do. For each of the inverse trig functions, we are going to restrict, I'm going to write it up top here. We're going to restrict each inverse trig function to two quadrants. So I'm only going to allow you to give me answers from two quadrants for each of the inverse trig functions. Okay, that's it. One positive quadrant and one negative quadrant. By positive and negative, I mean the ratios. So one positive ratio quadrant and one negative ratio quadrant. Okay, so that's what we're going to try to accomplish here. Now, it sounds very complicated and convoluted, but I promise you it's not as complicated as it may sound. So here's the idea. Let's start with y equals inverse sine. And we'll go through all six of the. Well, here's my coordinate plane. I know sine is the y coordinate. Here's what I need to do. On my coordinate plane, sine is the y coordinate. I need to pick one quadrant where the y coordinate is positive and one quadrant where the y coordinate is negative. And then the other two quadrants I'm going to eliminate. So I'm not going to allow you to give me answers from those two quadrants. Only the two quadrants that were chosen, one positive and one negative. So here's how this works. For all of the inverse trig functions, quadrant 1 is the positive quadrant, right? Because the y coordinate and the x coordinate are both positive in quadrant 1. So you're always going to get the positive answer or the positive ratio. You're going to pick the angle out of quadrant 1. What does change, however, is the negative quadrant. So here's the thing. If I'm going to choose quadrant 1 as my positive quadrant, then I can't choose positive or quadrant 2 because y is still positive there. Now, the other deal is you never choose quadrant 3 because we always try to choose a quadrant connected to quadrant 1 so that we can write it in a simple interval. So here, we're going to use quadrant 4 as our negative quadrant. So when I'm talking to you about the inverse sine function, you can only choose an answer for an angle from quadrant 1 or quadrant 4. But now I'm going to add insult to injury because we want to write this as one interval. So the problem is I can't write that y is going to be somewhere between 0 and 2 pi, like that in interval notation. Well, in my notation here, okay, in inequality notation. Because the problem is if I write this, then y can be anything from 0 all the way around to 2 pi. And that's not what I want. I only want answers starting in quadrant 4 and then ending up in quadrant 1. So just here, from here over to there. I don't want anything on the left-hand side. So what we're going to do is instead of quadrant 4 being angles from 3 pi over 2 to 2 pi, which they are, we're instead going to call them negative angles, from negative pi over 2 to 0, because that allows us to write this. So the inverse sine exists from negative pi over 2 to pi over 2. That takes me around quadrant 4, because negative pi over 2, I have to go down to here, negative pi over 2. So negative pi over 2 through pi over 2. These are my restrictions for the inverse sine. Okay? And the reciprocal functions are similar, but not exactly. Okay. All right. So now, let's talk about inverse cosine. Same idea. Inverse cosine. Cosine's the x-coordinate. The x-coordinate is positive in quadrant 1. They're all positive in quadrant 1. And now I'm looking for another quadrant that's attached to quadrant 1 where the x-coordinate is negative. One positive, one negative. Well, it's not there. X is positive here. Well, x is negative here, and that's quadrant 2. And that's fine. That's all we need. Okay? We never use quadrant 3. So, from here, I'm going to go around from there, from 0 to pi. So my restrictions for inverse cosine are 0 to pi. All right, let's talk about inverse tan. Let me erase some of this stuff that's here. Okay, inverse tan. So now, inverse tangent is a little different. Quadrant 1 is going to be used for the positive ratios. But now I need to pick one of the quadrants where it's negative. Quadrant 3 is never used. Well, tangent's y over x. So I need one positive where y is, or one of the coordinates to be positive, the other to be negative. But that's in both of these quadrants. In quadrant 2, it's y that's positive and x is negative. And in quadrant 4, it's x is positive and y is negative. So it could be either one. So what we actually do is we actually revert back to the graph of y equals tan x. On y equals tan x, the graph started at negative pi over 2 and the cycle completed at pi over 2. So in this case, we're going to use quadrant 1 and quadrant 4. Okay, quadrant 1 and quadrant 4. Now, inverse cosecant shares with inverse sine. Inverse secant shares with inverse cosine. But inverse cotan does not. Inverse cotan, we use quadrant 1, it's positive. But now if you remember back to our cotan graph, we started the graph at 0 and went to pi. So inverse cotan uses quadrant 1 and quadrant 2 for our answers, from 0 over to pi. Okay, so sine and cosecant use the same quadrants. Cosine and secant use the same quadrants. Tan and cotan do not. So that's going to be a key that you're going to have to remember. All right, so let's take a look at the summary here. So here's our summary. There are multiple ways to write the inverse trig functions. Some texts use the inverse sign notation. Other texts use arc sign. Both of them are used interchangeably. You can use either one. They mean the same exact thing. And these are your restrictions. Okay, so for inverse sine, you're working in quadrant 1 and 4. For inverse cosine, you're working in 1 and 2. For inverse tan, you're working in 1 and 4. For inverse cosecant, you're working in 1 and 4. For inverse secant, you're working in 1 and 2. And for inverse cotan, you're working in 1 and 2. And you see some of these restrictions here, like y can't be 0, y can't be pi over 2. That's because these are the angles that make, for example, cosecant undefined, or secant at pi over 2 is undefined. We don't talk about undefined here. Same thing with this. The reason why there's no equal sign here for arctan is because at negative pi over 2 and pi over 2, the x-coordinate is 0, so it would be undefined there. So we throw those out. Okay? And that's what you need to be able to work with, these quadrants. If you know these quadrants for the inverse trig functions, then everything else you get is right off the unit circle. All right? With a slight twist in quadrant 4. So here we go. Let's say I asked you for the arc cosine or the inverse cosine. Either way, you can write it either way, of 1/2. First thing you need to do is identify the quadrants that inverse cosine lives in. So inverse cosine lives in quadrant 1 and quadrant 2. Now, inverse cosine of 1/2. Which angle has 1/2 as its x-coordinate? Well, that's pi over 3. So that's the answer, pi over 3. It's done. You're only allowed to give one answer here. Okay? Let's try the arc cosine of negative root 3 over 2. So arc cosine lives in quadrants 1 and 2, from 0 over to pi. Inverse cosine of negative root 3 over 2. My answer is going to come from quadrant 2 because cosine's negative there. Okay, the x-coordinate's negative. Now, what's the angle where it's negative root 3 over 2? 5 pi over 6. There's my answer. It's all done. Arc sine of negative root 2 over 2. All right, now arc sine. Arc sine lives in quadrants 1 and 4. So from negative pi over 2 to pi over 2. I want to know where arc sine is negative root 2 over 2. So I'm going to go to quadrant 4 for that. Okay, but here's the issue. Normally in quadrant 4, the angle where it's negative root 2 over 2 on your unit circle is 7 pi over 4. But I can't call it 7 pi over 4 because I'm working on this interval from negative pi over 2 to pi over 2. So instead of calling it 7 pi over 4, I'm going to call it negative pi over 4. And that's my answer. Okay, so if you're working in quadrant 4, you need to give the answer as the negative reference angle. All right, negative reference angle. Okay, letter D, arctan of 1. 1. So arctan lives in quadrants 1 and 4. Tangent is y over x. So where is the y-coordinate divided by the x-coordinate equal to 1? Where are x and y the same? Tangent has to be positive. It's got to be positive 1, so the answer is going to come from quadrant 1. That's going to be at pi over 4. Arctan of negative root 3. All right, so arctan. Arctan lives in quadrants 1 and 4 again. So my answer is going to come from quadrant 4 because it's negative. Now, when I do arctan, here's what I do, to be honest with you. I know it's going to be one. It's got a root 3 in it, so it's got to be one of two potential points. It's got to either be 1/2 root 3 over 2 or the root 3 over 2 1/2. The question is, which one, when you divide y by x, will give you root 3? Well, you can do it on both, or you can just figure it out real quick. So root 3 over 2 over 1/2 would be root 3 over 2 times 2 over 1. Oh, this is the one that gives me root 3. But remember, my answer is from quadrant 4 because it's negative. And which point is this? So the x-coordinate is 1/2. That's going to be negative pi over 3. Right? This is the one for pi over 3. This is the one for pi over 6. Okay, and there's my answer. Inverse sine of 1/2. Same question as arc sine of 1/2. Inverse sine lives in quadrants 1 and 4. The angle is positive. So the answer is going to be from quadrant 1. The answer is pi over 6. It's all done. Okay, last set here. Inverse cosecant of negative 1. So cosecant lives in the same place as inverse sine. That's 1 and 4. Negative 1 is down here. That's at negative pi over 2. There's my answer, negative pi over 2. Arccotan of negative root 3 over 3. Now, arccotan lives in quadrants 1 and 2, different from arctan. The angle is negative, so my answer is going to come from quadrant 2. So again, I either have to do 1/2 root 3 over 2, or root 3 over 2, 1/2. Cotan is x over y. So if I do x over y on this top point here, 1/2 over root 3 over 2 would give me 1 over 2 times 2 over root 3. Cross out the 2's, I get 1 over root 3. Now if I rationalize it, I get root 3 over 3. Okay, so this is my point here. This is the point I'm using. This is the pi over 3 reference angle. In quadrant 2, I'm taking the angle off the unit circle. That's 2 pi over 3. Okay. Arcsecant of 2 is like finding the arccosine of a half. Same thing. So arccosine and arcsecant live in the same quadrants, 1 and 2. The angle is positive, so the answer comes from quadrant 1. Where is arccosine a half? That's at pi over 3. There's my answer. Arccotan of 1. Arccotan lives in quadrant 1 and quadrant 2. It's positive, so my angle is pi over 4. Where are the x and y coordinates the same? At pi over 4. Arccosecant of 2 over root 3 is the same as arcsine of root 3 over 2. So that's quadrants 1 and 4 for arcsine. It's positive though. Where's sine root 3 over 2? Pi over 3. There's my answer. And arcsecant of 1 is the same as finding the arccosine of 1. Where's the cosine 1? Cosine is 1 here at 0. Note, you cannot call this answer 2 pi. Okay, you can't call this answer 2 pi because we're working in only quadrants 1 and 2, and we're starting from 0 and working our way around to pi. Don't call this answer 2 pi. It's going to be marked wrong. Okay, and that's it. That's how we use the unit circle to identify inverse trig values. And as always, thanks for clicking.